Good day. Today we're going to talk about slopes of tangents and instantaneous rates of change, a topic so huge that it barely fits in the title down there. So that's how big we're talking today. The good news is it's still relatively short to do. Yesterday we took a look at secants, or whatever the last lesson we did was. Yesterday, the day before, this morning, I don't know. We took a look at secants and average rate of change. So we looked at the rate of change between 2 points to give us a straight line. Today we're going to look at tangents, which are lines that just glance off a curve, and they're going to give us the instantaneous rate of change. Now, to compare these two, I want you to think about driving a car. Now, if you drove 100 kilometers in 2 hours, your average rate of change, your average speed, would be 50 kilometers per hour. However, your speed's not 50 kilometers an hour the entire way. In fact, it's probably hardly ever exactly 50 kilometers an hour. Your instantaneous rate of change, or instantaneous speed, is given by the speedometer. And what it's really doing, and this is what the car is really doing, is it's figuring out an average rate of change over a minuscule amount of time. A very, very small amount of time, and saying what's the average rate of change over an interval so small that you can consider the two differences between the times to be one single time. So for instance, I can't find the instantaneous rate of change at 1 minute, but I could find it between 59.9 seconds and 60.01 seconds, or something like that. You get the idea. Now, if you want to think about how a secant and a tangent look on a graph, a secant literally connects 2 points. That's pretty straightforward. A tangent, if you want to think about getting onto a roller coaster and taking a broomstick, or in my case, a pen, because that's what I'm holding, and sticking it so that it's straight in front of you and goes straight behind you. That would be your instantaneous slope, your slope at a given point. And as you ride the roller coaster, you would hold it steady, but it would keep changing steepness as you go up and down. And because of that, it's going to keep changing its instantaneous slope, or its instantaneous rate of change. All right, why don't we just try to see how this works in actual math problems and go from there. I hate when I hit the wrong button. Hi again. So as I've already mentioned, a secant is just a line segment that connects 2 dots, or 2 points on a curve together, whereas a tangent is just glancing off the curve at a single point. Now, we have 2 methods of calculating tangents. There's a third one that you'll see in calculus, and maybe if we have time in this course, we'll take a quick look at it as well. The 2 methods we're going to use are both approximations. So what I want to do here is look at our first way of doing an approximation, and it's good. It's not fantastic, but it's good. And what we can do is we can basically draw a line that we think just glances off the curve at a point. And we'll look at the points 0, 1, and 2, or x equals 0, 1, and, negative 2, on a quadratic function. So y equals x squared. So what I'm going to do is bring up my ruler, because it's going to be handy, and say, can I match that graph at x equals 0? And if you'll forgive me for a second, I'm just going to zoom in a little bit because it's easier to see. And I'm going to try and make it so that at 0, yeah, it looks kind of flat to me. So if I draw a line that's tangent to the curve at 0, it's a little high, but I think the slope is correct. That would be the slope at 0. Now the slope at 1, again, I want to just glance the curve at that point. I think it's going to look a little bit like this. So right around 1, it's going to just glance off the curve. And then I want to do the same thing at negative 2, which is up here. And so when I do that, now you'll notice that here, the line almost looks straight over that short interval. So I think it's going to look something like that. Okay, now that I've drawn those on there, I'm going to zoom back out again. And I'm going to point out that at bye-bye thing. at our point 0 down here, our slope looks like a lot like it's about 0. So that would be the slope or rate of change at that point. Now this second line over here at 1, it looks like it goes over 1 up around 2. So I'm going to guess the slope there is 2. Now it could be my drawing or it could be the actual value is different, but it's around 2. And again, these are just approximations. They're not perfect, but they work. At least good enough for us for this part. And then over here at x equals -2, this looks like it's going to go, extend that curve down, I don't know, over 1 down, I don't know, 3 or 4. So I don't know, slope equals 3 or slope equals 4. Again, it's an approximation. It's hard to tell. And we'll see a better way of doing it in the near future. So that's those values there. Now, just to kind of give you an idea of slopes on a graph, I'm going to just switch over to Desmos really quickly. And I'm going to throw in a function, f at x equals x squared, the one we just looked at. And what I want you to notice is that even though the slope or the line is curved, if we zoom in enough at any given point, so let's take the point 1, 1, which is on the graph. If we zoom into 1, 1 enough, we're not really taking the slope of a curve. At this point, we really are taking the slope of essentially a straight line. I mean, that is so close to being a straight line, I don't think you'd ever tell the difference. And its slope does look like it goes over 1 and up 2. Now the values, well, over 1 box up 2 boxes. The ratio is 2 to 1. It's actually going over very, very little and up very, very little. But it's up twice as far as it is over. So I think our slope there of 2 is pretty good. Now, if we zoom back out and go over to where x was -2, which had a y value of 4, and we zoom in on that. Again, once you zoomed in enough, you'll see that the line is essentially straight. This is really no different than the idea that we live on a circular planet, but because we only see such a small portion of it, it looks flat. For those out there who still believe it's flat, please don't tell me about it. I can't handle that. And if we look at the slope of this, it seems to go over 1 and down 1, 2, 3, 4 units almost exactly. Again, it's not 1 and 4, but it's a ratio of 1 to 4. So going back, I think now that we've looked at it there, we can probably safely say that, yeah. Let's do this. I'm going to pull out my eraser. Now that we know better, and you don't have to change yours, but I think I can get rid of the m equals 3. It's no longer a guess. We're pretty sure that the slope there is equal to 4. Okay, so that's one way that we can find the slope of a tangent, or the instantaneous rate of change of a curve, is by basically trying to draw a line that glances just off the curve. And I'll tell you from experience, doing it with pencil and paper, it's easier said than done sometimes, especially if it's particularly vertical. If the line is very steep, it's hard to get it accurate enough that you're going to get a good answer. So, luckily, there is a mathematical way of doing it, and that is our method 2. And we're going to approximate the tangent by looking at a secant over a very short distance near a point. So if I take a look at the, again, we're just going to work with the base function f at x equals x squared, because it's easy to calculate x squared. If we want to look at the slope between 0 and 1, the average slope, or the average rate of change, that's just going to be rise, which is 1 squared minus 0 squared, over the run, which is 1 minus 0. And I think we can do that math mentally. That's 1 over 1 is 1. Now if we do it between 0 and 0.5, it's 0.5 squared minus 0 squared over 0.5 squared minus, sorry, not squared, 0.5. I'm making a mess. just 0.5 minus 0, which is 0.25 over 0.5, which is a half. All right. Between 0 and 0.1, the secant slope is going to be 0.1 squared minus 0 squared over 0.1 minus 0, which gives us 0.01 over 0.1, which is 0.1, which makes sense, 0.1 squared over 0.1. I'm going to actually use that trick over here. Between 0 and 0.01, it's 0.01 squared minus 0 squared over 0.01 minus 0, which is 0.01. So what do we see here? The slope is 1 between 0 and 1, but as we pull that second point back towards 0, so basically looking at the graph, the slope between here and here is 1, but as I pull this point back and back further, actually let me just really quickly zoom in on that a little bit. Let's get rid of the extra stuff around there. It's a little prettier. And I'll do it in red. Between 0 and 1, it forms that line. But as I move closer and closer to the 0, the secant gets closer and closer to being flat. And that's going to keep getting truer the closer I get to 0. Now, an even better way to do it is instead of going between the point you're looking at, in this case 0, and a number a little bit above it, you can actually go between a number a little wee bit below 0 and a little wee bit above 0. So this one is actually going to be 0.01 squared minus negative 0.01 squared over 0.01 minus negative 0.01. That's just change of height over change of x over, one more time, change of y over change of x. Now the top is 0, the bottom is 0.02, but either way, that slope is 0. And we kind of guessed that already, that the instantaneous rate of change at 0 is 0. Now, if you want to pause and try this one, we can do the same things for 1 and 2 and 2 and 3. Again, we're starting at point 1 and 2 and pulling that second value closer and closer to 1 so that we're at 1 and a little bit above 1. Or in the last case over here, two numbers very, very close to 1. So I'm gonna pause this just so that you don't have to watch me do all the math, because it's not hard. It's just a matter of plugging it in. And then I'll unpause it. And again, if you want to try this while I'm trying it, pause it and try it at the same time. That's cool. If not, I will be back in 1 second with completed answers. And ta-da, the magic of pause. Okay, so what I think you'll see here is that when you choose values around a point, so in this case, what we're really looking at is what is the instantaneous slope when x equals 1. If we choose 1 and a number above it, but we keep pulling that second number closer and closer to 1, we keep getting values closer and closer to our instantaneous slope. Our bad estimate was 3, and then as we pulled it closer, we got 2.5. We pulled it closer again, we got 2.1. We pulled it closer, we got 2.01. And then we did a trick where we went slightly above and slightly below, and we got exactly 2. So that is a pretty good approximation of a value that's exactly 2. So that's our slope there. Now, in the last 4 that we're doing here, again, I'm going to pause and you can try them or not. But I'm gonna pause it and do the values. But what I want you to see is that we're starting off with all these values around 2. We're going to start by going between 2 and 3, and then we're going to do 2 and a little bit closer to 2, and we're going to keep getting closer to 2 until we find the slope at 2. And I think what you'll see is that we should get a value of at least pretty close to 4, since that was our estimate using our other method. So I'm going to do that now, and I will be back in 1 second. And there we go. Our first one, which is going to be, of course, our worst estimate over here, gives us a slope of 5 between 2 and 3. And as we get that second point, moving closer and closer to 2, we eventually get over here, and we get a slope of 4 at the x value of 2, which is exactly what we predicted, again, going back up right there. So here's a mathematical way of finding the slope of a tangent, or at least the approximation of a slope of a tangent. It doesn't work. Now, it did work very nice for this quadratic. It does not always work this pretty, but that one's pretty good. I do want to point this out, and it may go without saying, but the first time I taught this to a class, they were very confused on the test why they all got the question wrong. They all said, Mr. Ray, you told us if we wanted to find the slope of a tangent, we just chose 2 points, the point and a little bit above it, or the point just below and just above, and find the difference of their squares over the difference of the values. That is not the formula for finding a tangent. The reason it works here is because we're specifically looking at f at x equals x squared. That's why we're doing the difference of the squares on the top. If we were doing the tangent of f at x equals x cubed, or x to the 4th, we would do the second value cubed or to the 4th minus the first value cubed to the 4th over the difference between them. So whatever function you're working with, you have to plug those values in. It doesn't always just work for squares. And to kind of get a feel for that, let's do this for f at x equals, or y equals x cubed minus 3x plus 1. And we'll find the slope approximately at the points listed here. We'll do it first of all by using the graph and trying to just approximate the value pictorially. And then we'll try it doing the mathematics, where we go just a little above and just a little below and see what happens. Okay, so in Desmos, I've already kind of got some of this stuff started so that we can see it all. First of all, I put in the function that we're looking at, y equals x cubed minus 3x plus 1. Not the prettiest function, but not the ugliest one. And what we want to do is see if we can estimate the slope of the tangent at a few different points. So the first point is at x equals negative 1. And when x equals negative 1, y equals 3. So I've actually plugged that point in already. It's right there. And then what I've done is I've taken the general equation of a line, y equals mx plus b, slightly different, just because it's easier to do this way. But I'm taking the basic line and I'm shoving it 1 to the left and 3 up so that it goes through the same point. So there's a straight line that goes through our point negative 1, 3. And my goal here is to modify the slope, which is the only real variable left in the relationship between x and y, until I can match it. And I think it's pretty obvious. It looks like it's at 0. So we can say that the slope is 0 at that point. And I'm going to write that over on the sheet, which is on the other screen. And when I come back to it, we'll see all those points written down. The next one we want to find is the slope at x equals 0. X equals 0 at the point 0, 1. So I'm just going to switch this to the point 0, 1. So we can see that's the point we want to find the slope of the tangent at. And that means I'm going to switch this to 0 and 1. And I realize 0 doesn't do anything, but I'm leaving it there for later. And then same as before, we're going to see if we can modify the slope of that until they match. And I know it's going to be negative, so I'll just go over like so. And turns out my m's not big enough here. I'll have to go down a little further. That's okay. And it looks like I'm going to get a match around there, give or take. And it looks like I'm very close to m equals negative 2.9. Zoom in a little bit. Okay, I can still see the difference up at the top here between the red and the green. So I have a feeling if I go right to m equals negative 3, they seem to cover up completely. So I'm going to say with some certainty that the slope at x equals 0 is negative 3. Do it again at x equals 1. X equals 1 there. So this point is 1, negative 1. switch this to minus 1, because the signs are different, and this one should be minus as well. So there's the point, the line going through it, and the slope there, again, I think is pretty obviously 0. And we have one more to try, and that's at x equals 2. This one's a little trickier. It's up here. It looks like x equals 2, y equals 3. It's very subtle to get it exactly on. There we go, 2, 3. I mean, I could have just plugged 2 into this formula up here and gotten that it's 3, but where's the fun in that? All right, so this is going to be mx minus 2 plus 3. And now I need to match that slope. I can go right up to 3. It's not enough. I know I'm going to have to go bigger, so I'm going to go, I think it's going to be between 10 and 15. If that doesn't work, I can always modify it. Oh, those two are close. Not quite touching. And this is where the visual model kind of doesn't work as well as the algebraic model, just because it's so steep that even a slight change in steepness means that I'm going to be off. So I'm going to keep... Oh, maybe it's not. Maybe it's a little less than 10. My mistake. 8 to 10. See if I get down a little bit. And somewhere around there, and I'm going to say it looks like around 9. So at x equals 2, I think the slope is going to be 9. All right, I'm going to switch back to our sheet there. You can see I've already filled in the answers that we just got, the slopes at those 4 points. And now the next thing is to do the equation by calculating the slope of the secant between the interval x minus 0.1 and x plus 0.1. So basically we're going to go 0.1 below each point and 0.1 above each point and see what that looks like. Before we actually do that algebraically, I'm just mathematically going to go back to the Desmos picture here. And essentially what I want to do, I have to probably zoom out a little bit. I think that's the right amount. If I plug in a point that we're close to x equals 3, or x equals 2, so I'm going to do between 1.9, and I'm going to leave the second number blank for just a second. We'll see why. 2.1. I need to figure out what it's going to be. Let me just turn off that line there. So at 1.9, again, I could use the formula, but it's 2.159. 2.159. And the other point at 2.1. Oh, I had it, and I lost it. .961. And what I'm really doing is looking for the secant between those 2 points. You know, let me actually get them in a different color just so they don't get confused with the other black dot there. They are in purple. And I think you can see that if I connected those 2 purple points, it's going to be very close to going through the black point. So that's all I'm doing, is picking one that's x value is a little bit higher and a little bit lower, and looking at the secant between those 2 points. So that's pictorially what we're trying to do. Now for the part that no one's going to be crazy about. What we can do here is figure out what the slopes should be algebraically by plugging in to the equation that formula up here. Bring up my red for a second. So what I want to do is say f at x plus 0.1 minus f at x minus 0.1 over f at x, sorry, yeah, get rid of that. It's change of y over change of x. Okay, so that's the formula. However, x is not, or f at x up here, not a particularly pretty function to plug in numbers like negative 1.1 and 0.9. And because of that, I am going to do it algebraically, but I'm going to choose the appropriate tool for that, which for me is not a calculator, but a spreadsheet. Okay, Excel's acting a little weird on me, but I seem to be able to record it in full screen mode, so that should do it. Now, let me just show you what I would normally punch into my calculator. I would pick my number, like for instance, I want to do the points around -1, and I want to go plus or minus 0.1. So I'm just going to plug those two numbers in there. Now what this over here, this cell here did, is it said, I want to take F1 and add F2, so that goes 0.1 above. And this one says F1 minus F2, so that takes me 0.1 below. So those are the two x values I'm going between. Now this one here says I want to find the value of the function at that point. Well, this is b1, so this is saying take b1 cubed minus 3b1s plus 1. So it's basically just doing it for me, plugging my number into the function that I was given, and this one's doing the same thing for that value. And then finally, this is just saying, what's the rise over run? What's the difference in the two f at x values, the two y values, divided by the difference in the two x values? And when I do all that, it gives me out the slope. So I am calculating this algebraically. I'm just choosing to use a tool that I think is more efficient than a calculator. And part of the reason I say that is because now that I can get that, I can write down that the slope for this one is 0.01 algebraically. But I can also now really quickly just say, okay, well, what is it around the point x equals 0? And when I enter that in, it changes all the information. I'm still going plus or minus 0.1. It's still doing the x values, 0 plus 0.1, 0 minus 0.1. It's still calculating f at x at those points, and it's still finding the slope based on that. So this gives me a slope of negative 2.99. I do it for 1. It gives me a slope of 0.01. And if I do it at 2, it gives me a value of 9.01. So now that I've gotten that far, let's just go back and compare that. I've written down the answers there, by the way. Compare that to what we got using the picture method. And yeah, 0.01 is pretty close to 0. Negative 2.99, negative 3, 0.010, and 9.019. Now in this case, I think the numbers that we got from the graph by looking at it pictorially gave us the actual results, and the others are approximations. The reality is they're both approximations. It's just because these happen to be whole number answers, our estimates here are probably better. If they were decimal answers, we probably wouldn't have guessed that accurately. But that's it. That's how we calculate slopes of tangents, either pictorially from a graph by just drawing a line that glances off the curve, or algebraically by looking at a point a little wee bit above and a little wee bit below. And by the way, for all these values in part B, or not part B, but the second part where we did it algebraically, we went plus and minus 0.1. I'm going to go back to Excel just for a moment again. Oops. And I want to show you if we actually took an interval much smaller, 0.001. That's pretty small. Then yeah, our slope around -1 Okay, that's scientific notation that basically says 0.000001. So it's 0. At 0, we get a slope of -3, exactly as we predicted. At 1, we get a slope of, again, 0. And at 2, we get a slope of 9. Okay, and these are accurate within about 1/1,000,000th. So I think that's pretty good. And if it wasn't good enough, we could just change this to give or take 0.000001, or as small as we want it to be. The smaller it is, the more accurate our answer actually will get. However, yeah, at this point, Excel's rounding off because it's so many decimal places before it makes a difference. So that is pretty cool. Yeah, there's our slope of 0 at 1 and -1. So anyway, that's how we can use Excel as a tool, as a calculator. You don't have to if you don't want to. On a test, if you're only doing it for one calculation, it's probably faster just to do it manually, to punch the numbers into your calculator and do it the long way. But I did want to show you that Excel is always a tool that you're welcome to use. Very cool to set this up too, by the way. And that brings us to the end of yet another lesson. So that's pretty much it for the main part of Unit 1. I will say that there are kind of 2 bonus lessons. We'll fit those in wherever we see fit. That might be the next 2 lessons. It might be the end. Still playing with the ordering just a little bit because we've got some interesting problems to take care of with the schedule the way it is. Anyway, I'm going to leave it there, and we will see you next time. Later.